Good morning. Again, I'm Marc Gomez. Hey, thank you very much for letting us come and talk to you about our Smart Lab concept. So let's talk about determining the potential for air change reductions. I'm going to share with you a story that unfolds over several years. Let's begin with the lab as a mechanical system. As Matt has been talking to us about, the mechanical system gives us a large opportunity for energy savings. So it's a great time to talk about safety and effective contaminant control. I think we all know that all HVAC elements in a lab need to be in balance. Things like fume hood placement need to be good. We need to have effective air supply and air exhaust locations so we can have good air mixing and avoid contaminant buildup. So let's take a little closer look at that diagram. So in this lab, we've got an air supply coming in on the left. Oops. And what we're hoping to achieve is effective air mixing as that air moves across from the left to the right and is exhausted out of the fume hoods. So it's important to evaluate air mixing in your labs, and for that reason, we have drafted an investigative protocol, which you have a copy of in front of you in your packets. And this lab air protocol correlates, we're trying to correlate lab air mixing with exposure monitoring studies. In fact, we're using helium bubble studies to evaluate airflow patterns. And David, in a little while, will talk more about that. So here's where we improved air mixing in a lab. You can see on the left side we have an air supply, and air is being forced down in front of our fume hoods, causing turbulence to that hood. So what we did is we installed a fabric air diffuser, and now we have air nice, evenly distributed into that space, no more turbulence in front of the fume hood. Let's talk about types of contaminant control. You probably know there's two types, primary, secondary. Local exhaust ventilation, capturing that contaminant at the source of generation is primary. We've been talking about secondary, air mixing and contaminant control, air changes. Fume hood, great example, primary source control. We've talked a little bit about snorkels and local exhaust ventilation. You can move them so they can capture that contaminant right at the source. Very good source control. And a glove box, another example, great source control. So recognizing that air changes are a secondary control, about 10 years ago, we started exploring the opportunity to safely reduce air changes. Our lab buildings, as you've seen, 10 years ago, they were running at 6, 7, 8, 9, 10 or more air changes. So we started talking about, can we reduce to 4? Can we reduce to 2 when unoccupied? So this reduction that UCI went through was a process that occurred over time, over years, because our goal, as you've heard, is to balance energy savings and safety. Back 10 years ago, we were attending Labs 21 conferences. If you've been, you know they talk a lot about reducing air changes. We hired an industrial hygiene and engineering consultant to help us talk through how to do this safely. We found a technology that facilitates this reduction that we'll talk about in a few minutes. And as you can see in that photo, we have an energy team that's been meeting for a decade, made up of environmental health and safety, facilities management, and others on campus. And we talk a lot about everything. And we talked a lot about air changes over the years. So we asked ourselves, is increased air changes safer? And in an article by our consultant, who's in the room, Tom Smith, he concludes that air changes as a metric for dilution is too simplistic. We've got to look at the things we've been talking about, lab air mixing, contaminant generation. Just paying attention to air changes could lead us to a false sense of safety. So over those years, the answer that we came to with is increased air changes safer is not necessarily. So we're trying to base our air exchange rate on contaminant generation. We review lab practices. As I mentioned, we're working hard for good air mixing in our labs. So our goal that began about a decade ago is to reduce overall air changes and then increase them via smart controls. And David will get into that in just a moment. So looking at the codes on air changes, those first two rows there, OSHA and ASHRAE, their ventilation rate range is about 4 to 12 air changes. When you start looking at the codes, they ask for 1 CFM per square foot, which equates to about 6 air changes in a lab with a 10-foot ceiling. And then when you get to ANSI and the American Industrial Hygiene Association, they start talking about air changes is not an appropriate concept for designing contaminant control systems. And the ACGIH, or American Conference of Industrial Hygienists, talks about ventilation depends on the generation rate and the toxicity of the contaminant. So we do lab benchtop risk assessments to determine the potential for safe air changes. It helps us answer that question. Can air changes be safely reduced? And we have 2 full-time industrial hygiene staff, one of them funded by utility savings, doing this. Excuse me. So when you walk into a lab, it's not easy to see if it's high or low hazard. In this case, we've got a fume hood. It's got a can of methylene chloride with a skull and crossbones, if you can see it. It's got compressed gases. It's got a hot plate. Looks a little scary. Is that high or low hazard? Looks high hazard, but we need a little bit more information. Here's a nice, neat lab, but all the work's being done on the lab bench. Is that high or low hazard? Again, we need a little bit more information. And here's a lab with a fume hood, but the work's being done outside the fume hood. So it's important to have a system or a process to do your lab benchtop risk assessment. And for us, step 1 is an industrial hygienist goes room to room and looks at the chemicals in use and how they're being used, talks to lab staff about all the procedures and processes that they do. They get to know the lab. The industrial hygienist then takes that risk assessment, those results, and compares it to hazard criteria. And all of this is entered into a database. And if there's concerns about a chemical or its use and follow-up is needed, we will not do an air change reduction. But if there is no concern about the use of the chemicals in those labs and no follow-up is needed, we'll go ahead and we'll do the air change reduction in that laboratory. In high-risk labs, for example, biosafety level 3 labs, labs with special ventilation requirements, no air change reduction. Our risk assessment looks at all of the chemicals of concern. We've listed some of the chemical families here for you. So fire codes often limit the amounts of flammables and pyrophorics that can be in a lab. And if we have situations where we exceed those amounts, of course, we will not reduce air changes. What we will do is we'll reduce the amounts of those flammables and pyrophorics. We work with our veterinarians in animal areas, and where we have animals 24/7, we do not do an air change reduction. This is because of the animal allergen concern and also for the good of the animals. So remember, step 1 of our risk assessment involved the industrial hygienist, and if there was a concern about the use of a chemical, we did not reduce air changes. So step 2 is an industrial hygiene follow-up for those chemicals of concern, and oftentimes this involves exposure monitoring studies of lab staff. And we try to work with them to improve their work practices. And after this follow-up for chemicals of concern, we find that frequently a ventilation reduction is possible because we can improve their work practices. But conversely, sometimes we raise those air change rates because we have not been able to. So in your packet, if you could pull out in your packet, there's the last page. It's behind the outline for Smart Labs. What I want to do is I want to briefly walk you through 2 scenarios so you can see how this benchtop assessment works. Number 1 there, it's the last page. In a molecular biology lab that performs immunology research, the researchers use an ethidium bromide solution. They pipette a few milliliters on the benchtop. Now, ethidium bromide as a powder can be an inhalation hazard, but in solution form, it has a very low vapor pressure, which means it does not volatilize much in air. And there are no listed occupational exposure limits for ethidium bromide. So the way this decision tree works is you start at the top, We identified the contaminant, it's ethidium bromide. We moved to the left, is this lab high risk? In this case, no. We ask a series of questions, is the contaminant acutely toxic? Is it an asphyxiant? Is it a strong odor producer? In this case, no. Is there a sensor for the contaminant? No. Is the contaminant a carcinogen or a reproductive toxin? Well, in this case, ethidium bromide is a mutagen. So the answer to that question is yes. So then our industrial hygienist does a follow-up. And in that follow-up, they found that in this case, the ethidium bromide powder is used in a fume hood with appropriate personal protective equipment, and there are standard operating procedures that dictate that. So we had a level of comfort and no complaints from the lab staff. So in this case, we were able to reduce the air changes in that lab. It's an example of how the diagram works. If you look on the back page, I'm going to walk you through a second scenario, a little bit more complex. So in the second scenario, where we have a chemical engineering lab that researches the synthesis of nanomaterials, and lab staff use hydrogen sulfide in a chemical deposition oven. Now that hydrogen sulfide flows through one end and exhausts out the other of that oven. Now initially, this process was performed on an on a lab bench, open lab bench. So again, we begin at the top of that diagram. The contaminant in this case is hydrogen sulfide. We move to the left. Is it a high-risk lab? No, it's not. But hydrogen sulfide is acutely toxic, and it's also a strong odor producer. So the answer to that question is yes, and we move down, and we do not do a ventilation reduction. Now, over time, David actually worked with this lab, and we were able to install hydrogen sulfide alarms in the lab, and we moved that oven into the fume hood and developed standard operating procedures around that. So because we have the alarm system and the hazardous work being done in the fume hood, we were able to eventually reduce air changes. Do you happen to know? I don't think the levels are high enough. No, I don't believe so. Regular chemical fume hood. The volume is not high of the hydrogen sulfide.
And it's not exhausting. The only reason why we put it in the hood was to, as a backup for just in case air.
So it's a low volume.
In normal operation, it's not emitting hydrogen sulfide at all.
So we also have a overnight setback decision tree. But I want to move along and ask David to come up and talk a little bit about centralized demand controlled ventilation.